All right, everybody, welcome to the fourth screencast for Chapter 5. In this one, we're going to return to a concept we've talked about a little bit already, the idea of goodness of fit, and basically how well does the regression fit the data. But now that we have multiple variables, there's going to be a little bit of a difference here. So the variance of the beta 1 hat distribution in the multivariate model is very similar to the variance of beta 1 in the bivariate model. So if you recall this picture that we've drawn a lot, the probability of any given beta 1 hat is the vertical axis. Particular values of beta 1 hat are the horizontal axis. We know because beta 1 hat is a sample mean that it has a normal distribution. So pretend that's normal. There. So the distribution of beta 1 hat is distributed as normal, and it's got a mean, which is the expectation, if I can get this to draw, of beta 1 hat. And what we hope is that if we're unbiased, that the expectation of beta 1 hat equals the true beta 1. And one of the big things we're concerned about, especially when it comes to testing the statistical significance of a particular beta 1 hat, is the width of this distribution. How wide or skinny is it? So the variance, right? The beta 1 hat is distributed normal with a mean, that is the expectation, and then it has a variance. And so we want that variance to be as small as possible, because the skinnier the the distribution is, oh man, I cannot get it to work. The skinnier, there we go, the distribution is, the more likely it is we'll be able to reject the null, right? Because we'll get a beta out here and we'll be able to reject that because its probability is low, meaning it will have a high t-value or a low p-value. So you can still just think about it that way in your head, because that graph still applies, because beta 1 is still the effect of a 1 unit increase in x1 on y. And so in this section, again, we're going to do the thing where we're going to kind of assume away some of the other problems so that we can isolate one particular problem. So here we're assuming there's no heteroscedasticity, or we're assuming the errors are homoscedastic. And also we're assuming the errors are not correlated with each other. All right. So this is the new formula for the variance of beta 1 hat. And for almost all of this in this section, yes, this is technically the definition for any beta, right? But what we really care about is beta 1, right? So in other words, if we have this model, this could be the variance for beta 1 hat or beta 2 hat, right? Depending on what we put for j here. But almost always what we are going to care about is beta 1 hat, right? We don't really care about the variance of beta 2 hat or beta 3 hat or beta 4 hat if the model had that many variables. So for all of this, it's technically true that j, it applies to any variable, the coefficient on any right-hand side variable in the model, the coefficient on any independent variable in the model, to say it another way. In reality, beta 1 is what we're concerned about. So if it makes you feel better to simplify this a little bit and just put ones everywhere in your copy of the notes, that's perfectly fine, and it may help you with the understanding here. But again, this is the variance of beta 1 hat in a multivariate model. Now, everything about this looks very similar to the variance of beta 1 hat from equation 3.9 in the textbook. All right. In fact, let me bring that up. So let me bring that up. So here on the right-hand side, the left-hand side, this was the measure for the variance of beta 1 hat when it was a bivariate regression, and here it is for a multivariate regression. And let me zoom this up just a little bit. And we can see that they're very similar expressions. The n is the same. So remember what that meant over here, right? And remember what this is, just as I said earlier, I forget when I'm doing the screencast, you can just rewind if you forget what I said, but let me just go ahead and repeat it. We're talking about the width of the hypothetical distribution of beta 1 hat, right? That's what this variance is about. So this was the number of rows in your data set. So the bigger that was, the skinnier the variance became, right? Because if you increase the size of the denominator of a fraction, the size of the fraction gets smaller. This was the variance of x. This was how much dispersion there was in the x1 variable, the independent variable of interest. Is it really, really spread out, or is it very, very narrow, the measurement on that variable? The more spread out it is, the lower the variance. So having a x1 with a lot of variance was good, actually, because it shrinks that hypothetical distribution, and that therefore makes it easier to reject the null hypothesis, right? And then the numerator here is just basically a measure of the average sum of the squared errors. So on average, how far are the dots from the line? Over here, it's a similar thing, right? Everything, all of these terms are the same. Let me just mark them. N is here, N is here. The the distance of the average dot from the best fit line, that's right here, that's the same. And then this part is the same. The variance of x is the same, all right? I didn't put an x here for times, but this is n times variance of xj. And remember, you can just replace that with a 1 for this discussion. The only thing that really differs is this 1 minus r squared j. So what is going on here with this 1 minus r squared j? All right. Well, this is an r squared, much like the r squared we already know. In other words, it's the amount of the variance in the left-hand side variable that the right-hand side of the model explains. We called this the goodness of fit before, that r squared. So in other words, if you have a regular regression, y equals beta naught plus beta 1, x1 plus e. This was x1, xi, sorry. This is the amount, an r squared for this regression would be the amount of variance in y that x explains. And what is this r squared? Well, this is like that, but it's the r squared from an auxiliary regression, right? Remember, the auxiliary regression is a tool we use to look at the relationship between two variables, but we're not necessarily looking for what is the effect of a 1 unit increase in x on y, but we can still use a regression to look at other things. And we already know regressions well, so why not use that tool? So r squared j is the r squared from an auxiliary regression. It's a regression where xj, x1 for us, is the dependent variable, and all the other x's are the independent variable. So it's an auxiliary regression with your independent variable of interest as the left-hand side variable. So x1i is going to be on that side, right? And then all the other x's in the model will be on the other side. So here is the main regression that I want to talk about. So this has 3 independent variables. x1 is the independent variable of interest, all right? And what I want to know for r squared j is how correlated are these variables with one another, these 3, x1, x2, and x3. And so what I do is I run this regression. And here, just as in the previous sections, we picked different Greek letters for the slope coefficients and the intercept. I'm doing the same thing here with this gamma, these lowercase gammas. So this is x1i as the dependent variable. And then this is like beta naught, but we're not going to call it beta naught so we don't get confused. It's gamma naught plus gamma 1, which is the correlation between x2 and x1. And then gamma 2, which is the correlation between x3 and x1. And then, of course, there's an error term. All right. So this r squared 1 or r squared j back in the this expression, this is how correlated is the x1, again, put in 1s everywhere here. Let's make this a 1. and a 1, and a 1. How correlated are all the other x's in the model with x1? That would be what this r squared would be. All right. And so what we want to think about is, well, what does that do to the variance here? If they're highly correlated, does the variance get bigger or does it get smaller? All right. That's what we want to investigate. So if all of these x's are highly correlated, what does that do to the variance of the beta 1 hat distribution, right? We want it skinny. We always want the beta 1 hat distribution to be as skinny as possible. That gives us the highest chance of rejecting the null hypothesis, all right? And just to show you for completeness sake, r squared 1 is the r squared from this regression where x1 is the left-hand side variable. R squared 2 is the regression when x2 is the left-hand side variable, and all the other x's are on the right-hand side. The same thing with r squared sub 3. It would be the r squared from an auxiliary regression where x3 is the left-hand side. But really, we're just going to mostly care about this one. We're going to care about this r squared sub 1. We're going to want to know how correlated is x1 with all the other variables in the model. So what happens here? Well, let's think about what if r squared sub j, and again, let me go ahead and just put in 1s for everything. 1 here, and 1 here, and 1 here. What if r squared sub 1 was big, right? What if r squared is close to 1? Remember, r squareds are the amount of variance that the right-hand side explains about the left-hand side. And 1 means it's perfect, right? It means 100% of the variance in the left-hand side variable is explained by the right-hand side. An r squared of 0 means 0% of the variance in y is explained by the right-hand side of the model. Okay? So if r squared is big, if there's a lot of correlation between x1 and the other x's, then what does that do to this? If this is 1, then this becomes 1 minus 1. That becomes 0. This term becomes 0 if r squared is big. So let me just write that. If r squared sub 1, the r squared from the auxiliary regression, is 1, then this becomes 0, and this whole bottom term becomes 0. Well, what happens as the denominator of a fraction gets close to 0? We don't want to think about what if it is 0, because if you divide by 0, you destroy the universe, right? So let's think about what if r squared sub 1 is 0.99999, right? Really, really close to 1. Well, then this becomes almost 0, and so multiplying anything by almost 0 makes the entire term almost 0, and that makes this an incredibly big number. The overall variance would get huge, right? And you can think about it this way. Think about going from 1 over 1, right? Going to 1 over 1 half, 1 over 1/3, 1 over 1/4, 1 over 1/millionth, right? The overall value of the fraction is getting enormous. So, bottom line, the more correlation there is between your x variables, the wider the hypothetical distribution of beta 1 becomes, all right? That's bad, right? So high correlation amongst your x variables is bad and can make it hard for you to reject the null hypothesis, all right? So that will make standard errors big, and it makes statistical significance hard to find. All right, so you don't want to throw every possible x variable into the right-hand side of the model. You only want to include x's as control variables where you know that x is correlated with your x1 of interest and your y. You don't want to just include every variable possible, because that will blow up the width of your hypothetical distribution, and it will make your standard errors very big, and it will make statistical significance hard to find. All right. Now we have a particular name for this. This idea is called multicollinearity. It means your x variables are multicollinear with one another. Perfect multicollinearity means that all the other x's perfectly explain your x1. That's the worst situation. That's the r squared j, or r squared 1, equal to 1. And it makes your the variance of the beta 1 hat distribution infinity, right? So that's really bad. So the term 1 over 1 minus r squared is sometimes called the variance inflation factor. All right. So this is how bad is the high r squared hurting you, or how little is it if it's a small r squared sub j, right? Again, this is the r squared from the auxiliary regression, where the jth variable, again, just put ones in, where the first variable, how correlated is it with all the other x's? And so high multicollinearity is bad. It causes the hypothetical distribution to be wide. If we have a lot of data, that might not be too big of a problem as long as it's not perfect. But multicollinearity doesn't cause bias, right? It's not moving the hypothetical distribution around, right? If we're unbiased, right, the expectation of beta 1 hat equals beta 1 if we're unbiased. What it does is it makes this wider than it otherwise would be, which makes it hard to reject the null hypothesis. So adding a lot of right-hand side variables for no good reason can cause you to lose statistical significance. So with high multicollinearity, you can have a problem. Now, sometimes you're going to end up in a situation where you have to have it, right? So let's say you need to include certain control variables because if you left them out, you would be biased, right? You would be shifting the hypothetical distribution off of the truth. So you've got to include it. But by including those control variables, you get high multicollinearity. Well, there's a test you can do that will let you test multiple variables at a time. And I'm not going to really go into that for this situation, mainly because we're not doing a lot of the projects this semester. But if you run into that situation, I'd be happy to talk with you about that. You've included control variables, you do the test for multicollinearity, you have it, you have multicollinearity, what can I do now? Well, there's a joint hypothesis test you can do where you test the significance of multiple beta coefficients. But perfect multicollinearity is when the r squared j, again, what we care about is r squared 1. We care about the r squared of x1 as the right-hand side, the left-hand side variable. This hypothetical distribution, sorry, I need to do gammas here, of gamma naught, gamma 1, x2 I plus gamma 2, x3 I plus epsilon, right? This r squared is the r squared from this regression. When it's 1, the beta 1 variance is 0 in the denominator and it's infinite. I guess I already said that, so now I've said it twice. There we go. But this is not the same thing as plain old r squared. Plain old r squared is still the r squared from the original regression, right? So that would be the r squared from this original model. R squared, no subscript, is the amount of variance in y that all of these x's explain. All right, it's the same as it was for the bivariate regression. All right, and we care about it just as much as we did before. We don't care about it. The r squared is not very important for us. This r squared, the r squared for the main regression. We don't care about making it really big or really small. We don't care in and of itself about how much variance in y all of our x's explain. What we care about is isolating the effect of one x1, our chosen x1, our independent variable of interest on y. All right. Back in the day, people thought r squared was a big deal, so people would add a whole bunch of x's to pump up their r squared, right? But that ends up hurting you. It makes it hard for you to isolate the effect of a given x1 on y, all right? So there's this thing called an adjusted r squared that would kind of penalize you for including too many x's. We don't need to worry about that in OLS because we're not going to be doing that. We're not going to be throwing every x in the world into our regression in order to get a really high r squared. It's just not what we are about in this class. We're trying to isolate the effect of one x on y. So we're going to include other control variables, other x's, only if those things are correlated with our x1 of interest and why. And only for that reason. We're not going to throw extraneous things in. So what happens if we do include an irrelevant variable? It's not going to cause bias, but it's going to make our estimates less precise. It might increase r squared sub j, and it's going to definitely increase r squared, more than likely, but it's going to increase r squared sub j, and that's going to inflate the width of the hypothetical distribution. Adding irrelevant variables makes it less likely that we can reject the null. Adding them makes it hard to find statistical significance on one particular variable. That's bad. We don't want to do that artificially. So here's a little case study we can walk through. So does having an independent judiciary in a country help stop human rights abuses? So our dependent variable is going to be human rights measure. This is an index that different groups put together to rate a country's human rights. Same thing with judicial independence. This is an index. These are sort of like the indices you might have seen in Saravia's Moral Foundations class, these indexes of economic freedom. But these are different country-level indexes for other things. One is for human rights, and the other is for how independent is the judiciary. In the U.S., we have a purposefully independent judiciary. It was written that way in the Constitution, and then it was codified as being an independent judiciary by Marbury versus Madison back in the early part of the country. But not every country has that. In some countries, the highest court in the land the people can be fired from it at any point by the executive branch or the legislature. And then our control variable here is going to be log GDP per capita. You might think that countries with more wealth per person will be more likely to have judicial independence and more likely to have human rights. So that's the basic model, but let's think about another variable, democracy. Notice, the more democratic a country is, the more likely it is to have judicial independence and human rights. All right. So if we were to run this model without democracy, we might have omitted variable bias. In other words, our estimate of the effect of judicial independence on human rights might be biased. So let's look at some scenarios so we can see that that is, in fact, a problem here. So let's just look at this version of the model. So this is the one where we've left out democracy. All right. And we might be tempted to say that, yes, it's statistically significant, and then a 1 unit increase in judicial independence leads to an 11-point increase in human rights scores. All right. But now look at this version of the model, the one where we have included democracy as a control variable. Because by leaving it out, because democracy is correlated with judicial independence and the human rights scores most likely, we would have had a biased result. So what does it look like now that we've included this control variable? Well, notice now we are no longer statistically significant. T here is not anywhere close to being larger than 2. So this would have been wrong. We would have been in error because we forgot to account for the omitted variable bias. All right, so we already talked through all that, but you have it here for your slides. So here's the issue. If you ran the test for multicollinearity, we would have it. The variance inflation factor, which is the test for multicollinearity, would be 1 over 1 minus, and this is the r squared for a regression. So this would be the r squared sum 1 for the regression, for the auxiliary regression. And I would have judicial independence for each country sub I on the left-hand side. I'm going to go with the gammas again just to make sure we don't get confused with the betas. And this would be gamma 1, and this would be the GDP. And then gamma 2 here for democracy plus the error term. All right. So the r squared for this would be what the value is on the next slide. And so it's going to be 0.553. And so when you plug that in, that gives you 2.24. That's a large variance inflation factor. The variance of the coefficient for wealth is 2.24 times larger than it would be. So it's a multiplicative effect. So my beta 1 is 2.24 times bigger than it should be. All right. And notice it also made it where we could fail to reject the null hypothesis. The issue here is, democracy, per capita GDP, and judicial independence are all highly correlated with one another. So it's preventing us from teasing out the independent effect of judicial independence. All right. So we're not going to have a lab on this, but if you do need to know in the future on how to run this test, please just ask and I'll be happy to provide the code for you. The template online actually already has the code for that. So if you run into that, you've already got an example there that shows you how to do it.